Hello everyone. So in the previous session we have learned the theorem on a measurable sequence of function. So by using the corollary of that theorem we are going to prove the Ergoff's theorem. It is called as Ergoff's theorem. Statement is if E is measurable set with measure of E less than infinity and Fn is a sequence of measurable function which is converging to F almost everywhere on E, then for a given neta greater than 0, there is a set A with measure of A less than neta such that Fn converging to F. So in the previous session what we have proved is, so let me tell you the glance of that. Suppose if F is a sequence which is converging to, Fn is a sequence which is converging to F, and moreover difference between Fnx and f of x will be less than epsilon for all n greater than equal to n and for all x belongs to E minus A. So this is the corollary of the theorem what we have proved in the previous session. I'll just tell you once again, if Fn is a measurable sequence of function which is converging to F, then magnitude of Fn of x minus f of x will be less than epsilon for all n greater than n and for all x belongs to E minus A, and moreover where measure of A will be, where A is a subset of E and A measure of A will be less than delta. This theorem I have proved in the previous session. So we are making use of the same theorem to prove the Ergoff's theorem. So let me prove the statement. Now to prove this statement we have to use the corollary as I already said. So let me prove. So we prove the theorem by using the corollary that we already proved. So using corollary with epsilon is equal to 1, I am going to take epsilon, whatever the value epsilon I have, so I am going to take epsilon as 1 and delta as neta by 2. Right? Why? Because we have to prove the theorem for measure of A is less than neta. So on neta is a given quantity, so we have taken delta as neta by 2. And moreover here in the theorem I have told you that A is subset of E. So here let me take A1 as subset of E. And measure of A1, since I have taken A, so obviously measure of A1 will be less than delta. In place of A I have chosen A1. Fine. So let me replace in the theorem statement. That is what I am going to write as Fn of x minus f of x will be less than 1. Why? Because epsilon value is 1. And for all n greater than or equal to n1 and for all x belongs to E minus A I have. In the corollary theorem we have E minus A. So in place of A what I have taken, it is A1. So let me replace A with A1. Fine. So just in place of A I have taken A1. Fine. So as x belongs to E minus A1. So let me take E minus A1 as E1. Just a representation. What I have done is I have considered the previous theorem. I have already proved this in the previous session. Please go through that. So I have taken epsilon value as 1 and delta as neta by 2. Anyhow it is very small quantity. And instead of A I have taken it as A1 subset of E. Then measure of A is less than delta. So in place of A I have taken A1. So I have substituted epsilon value as 1 in the statement and I have denoted E minus A1 as E1. So it is just a generalized case. So first step I have taken this. Next let me take epsilon as 1 by 2. Here epsilon I have taken 1. So let me take it as 1 by 2. Then delta will be neta by 2 square. I am reducing the quantities epsilon and delta. For the first time epsilon 1 and delta n by 2. Second time epsilon 1 by 2 and delta neta by 2 square. Fine. So let me replace A1 with A2. A2 is subset of E, then measure of A2 will be less than delta, and moreover Fn of x minus f of x, I am skipping the statement, you have to write it in a statement form, just I am writing mathematical form, will be less than, in place of epsilon, see here Fn of x minus f of x less than epsilon I have. So for the first time I have chosen epsilon as 1. So now I have taken epsilon as 1 by 2. So 1 by 2. I am reducing the quantities. You can note that 1 by 2 is less than 1. So I am keep on reducing it. For all n greater than or equal to, let me take it as n2. And for all x belongs to, you can guess now, E is, first element is E, next element E1, next element is E2. So it continues. So E minus A1 I have already done. So next element is E1. So E1 minus, instead of A1 what I have taken here, A2. Let me assume this set as E2. So for the first case I have taken epsilon as 1, epsilon as 1 by 2 for the second case. So if you continue the same, that is by taking epsilon is equal to 1 by 2 square, 1 by 3 square, that is we are going to reduce the values of epsilon for the third and fourth step. So when you continue, so instead of writing all those, let me write. So when you continue this process, for the kth stage I can write So delta will become, since in the first case it is neta by 2, in the second case it is neta by 2 square. So in the third case it is neta divided by 2 cube. Third case. In the fourth case it is neta divided by 2 power 4. So we are doing it for kth stage. So I can write it is neta divided by 2 power of k. I am generalizing it. Fine. And in the second case I have taken a set A2 which is subset of A. So for the kth stage I have taken AK. Fine. So AK will be subset of E, and moreover measure of A2 in the sense, if for the k stage it will be measure of AK less than delta. In the sense measure of AK, what is the value of delta here? Less than neta divided by 2 power of k. Now this step will become, that is fn of x minus f of x will be less than 1 divided by 2 in this case. In the third case it is 1 by 2 square. In the fourth case it is 1 by 2. Right? So when you continue the same process, so I can write this as 2 can be written as 1 by k. For all n greater than or equal to, in place of n2 I can write nk, and for all x belongs to e1 minus a2 can be written as, generalizing it, so ek minus 1 minus ak. Further this is represented by e2. So I am going to represent this with ek. Right? I have generalized the case for the first stage, second stage, and for the generalized case, that is k. Now what I am going to do is, let me set the value of A as union of all ANs. Fine. Now let me apply measure on the above step. So you will get, as I already told you, let me apply the monotonic property and translation invariant property. As per that, when you are going to change union to summation, equals will become less than or equal to. So you will get less than or equal to summation n is equal to 1 to infinity measure of an. Further, what is the value of measure of AK? Here measure of AK is less than neta by 2 power of k. Here measure of an I have. So I can write this as less than summation. Let me write summation as it is. N is equal to 1 to infinity. Measure of an is none other than, it is less than neta divided by 2 power of n. Since I have k here, that is why I have written neta divided by 2 power of k. But in the second case I have an. In place of AK I have an. So I have written neta divided by 2 power of n. Now I can write neta divided by 2 power of n as neta. Directly I can write this as neta. Why? Because I have already simplified such kind of problems in so many theorems. Anyhow, I am not going to repeat the same for all. Just here I am going to simplify. If you keep on writing all these steps here, it may elaborate. So instead of writing, I can write directly. Why? Because see here summation n is equal to 1 to infinity neta divided by 2 power of n. So neta is independent of n. So let me take neta as constant. Outside I can take summation. So I'll get 1 divided by 2 power of n. Now let me apply n is equal to 1. For the first time you'll get 1 by 2. Second time 1 by 2 square. 1 by 2 power 3. So it will continue. Now I can take 1 by 2 common. So you will get 1 plus 1 by 2 square plus 1 by 3 square plus so on. Fine. Now how can I write this as? See here you have 1 plus x square. I'm sorry, it is 2 cube, right? 1 plus x plus 1 plus x square plus so on. So when you have such kind of term, you can write this as 1 minus x power of minus 1. So you can write this as 1 by 1 minus 2 power of minus 1. Now further neta into 1 by 2 into 1 minus 1 by 2 is 1 by 2 whole power of minus 1. Now 1 by 2 I can write this as 1 by 2. Right? Why? Because suppose if you have a power of minus 1, I can write this as 1 by a. So that is what I have done here. Now 1 by 2 get cancelled. You will get neta here. See here, a power of minus 1 when I have, I can write this as 1 by a. So 1 by 2 get cancelled, you will get neta. In the sense, when you have summation n is equal to 1 to infinity, neta divided by 2 power of n can be written as neta. So that is what I have done here. Neta divided by 2 power of n, I have written it as neta directly. So no need to write all these steps, and further it is not given in the notes. It is explaining just for your reference. Fine. Now I have taken this value as neta as per the simplification I have done. So further, if you consider a set E minus A, then we can write this as E minus what we have assumed A as union of all AN. So I can write A as union of n is equal to 1 to infinity AN. Right? Again, if I am going to rewrite this, I can write this step as, I can write this as intersection of all E minus AN. So when you are going to take this inside, union will become intersection. Right? Now This is for one case. Let me apply for generalized case. Like if it is true for all number of sets, it will be true for all en and en minus 1 number of sets. Like something like if a property is holds good from a numbers like 1 to 9, it will be holds good for 8th number also. It will be holds good for 7th number also. Likewise, if the property is true for all e number of sets, it will be true for all ens and en minus 1 number of sets. So I can write this as intersection n is equal to 1 to infinity en minus 1 minus an. So in place of ek minus 1 minus ak, I have assumed n minus 1. That is for all generalized case I have taken. Fine, this is for only one collection. See here in the first stage I have taken e minus a1, e1 minus a2, and similarly in the kth stage I have taken it as ek minus 1 ak. So similarly here for the nth set, in place of k what I have taken is n. So I can replace en minus 1 minus an by en, right? So in place of k I have n. So I can write this as intersection n is equal to 1 to infinity en. Clear? So what I have proved is e minus a can be written as intersection of all the ens. Now let me take an element x which is in a set e minus a. So if you are going to choose one element, say x, which is in a given set e minus a, we can write this as x belongs to en. En is a largest set where we have a set e inside en, right? So if x belongs to en e minus a, so if you are removed one of the set a from this set, then x will be in en, right, for all n. So if this was the case, as from the previous corollary what we have done, if x belongs to en, all the elements will be satisfying the condition fn of x minus f of x will be less than epsilon, right? So I am going to apply the same property now. Fn of x minus f of x will be less than 1 by n for all n belongs to n, right? Now suppose if we choose large number of values for n, obviously 1 by n will become very lesser value compared to epsilon, right? So if you keep on increasing n, it will goes to infinity. 1 by infinity will become 0. That is as you increase the n values, the value of 1 by n will be keep on reducing. At some particular instant 1 by n will be less than epsilon. So I can write this step as fn of x minus f of x will be less than epsilon for all n belongs to, or for all n greater than, so it is for particular value. So whatever the values you are going to consider greater than one value, let me take n of n as capital N, it will be true. And for all x belongs to what we have assumed as e minus a. Meaning of this is, as I already told you, definition of convergence, when magnitude of fn of x minus f of x is less than epsilon, what it says as per the corollary, fn of x will be converging to f of x uniformly on e minus a, right? Uniformly on e minus a. Why? Because I have chosen an element in the set e minus a, and that is what we required to prove is we have to prove that sequence fn of f is converging to f uniformly on e minus a. Clear? I am repeating once again. I have considered the previous session corollary. For the first case it is epsilon is equal to 1 and I have chosen delta as neta by 2. Clear? For the second stage I have chosen epsilon as 1 by 2 and delta as neta by 2 square. So if you keep on giving values for epsilon, so you will get n number of stages. So for particular stage let me take it is k. So for kth stage I can write delta as neta divided by 2 power of k. So here an element I have taken a subset of e as a1 and here a2. So in the third stage it is a3. So in the k stage it is ak. Similarly, I have replaced wherever it is necessary and have assumed a set A as countable union of all the sets and I have applied the properties so as to get a sequence fn of x is converging to f of x uniformly on e minus a. So this is what the required proof is. Clear? Now let me discuss one more important concept. Next concept is Lebesgue integral. So far we have studied Lebesgue outer measure, Lebesgue measurable functions and Lebesgue sets, right? So in this session let me discuss Lebesgue integral. So we can also say Lebesgue integrals as Riemann integral. So one and the same. Riemann integral is also called as Lebesgue integrals and it is important concept. It is asked in the year 2017. So Lebesgue integral in the sense, so we already know that step function in this. What is the meaning of step function? If we define a function from closed interval ab to any real number r, so we can divide the partitions of closed interval ab, right, in such a way that like some x0 will be less than x1, will be less than x2. So if you continue this, will be less than xn, and last value will be b. And if you're going to set capital Mi as supremum of all the function f of x, and this x will be belongs to any of the interval, closed interval xi minus 1 and xi, and if you define small mi as infimum of f of x such that x belongs to xi minus 1 and xi. So let me define once again. Lebesgue integral is same as what we say Riemann integral. Fine. So for each, as I already told you, suppose if I have a function f from ab to r which is bounded function, and we can divide this closed interval into n number of partitions, something like this, then we can define capital Mi as supremum of fx and small mi as infimum of fx. Then we can define upper bound of a partition p with respect to f. We say this as upper bound of partition p with respect to f is given by sum of all capital Mi's taken over the interval xi to xi minus 1. Fine. So sum of all supremums, I can say. Supremum is another than Mi. And similarly, lower bound of partition p with respect to f is given by I is equal to 1 to n sum of all small mi's, that is infimum over the interval xi to xi minus 1. This is called as upper bound of a partition p with respect to f. This is lower bound of partition p with respect to f. So m is the supremum of all the values of a function. Small mi is the infimum of all the values. Upper bound is sum of all the supremum values. Lower bound of a partition is sum of all infimum value. So if this was the case, then upper Lebesgue integral is denoted by this, and lower Lebesgue integral is denoted by this. Fine. And is given by, let me write upper Lebesgue integral. So upper Lebesgue integral is none other than infimum taken over all the upper bounds. Infimum taken over all the upper bounds. So it is represented by upper bounds. We can also say it is upper Lebesgue integral or upper Riemann integral. So upper Riemann integral is none other than, when you are going to take infimum over all the upper bounds, you will get upper Riemann integral. Similarly, lower Riemann integral is none other than, it is reverse, supremum of all lower bounds. Supremum of all lower bounds. I am repeating once again. This is called as upper Lebesgue integral or upper Riemann integral. This is lower Riemann integral or lower Lebesgue integral. So upper Riemann integral is none other than infimum taken over all the upper bounds. Lower Riemann integral is none other than supremum taken over all the lower bounds. So this is what the definition of Lebesgue integral. So it is also called as Lebesgue or Riemann integral over a closed interval AB. And so it is denoted by Riemann integral of f is equal to upper Riemann integral which is equal to lower Riemann integral. Meaning is, when the value of upper Riemann integral is equal to lower Riemann integral, it is integral symbol. So if a function value whose upper Riemann integral will be equal to lower Riemann integral, so if they both are equal, we can say a function is Riemann integrable. So it is denoted by Riemann integrable of a function f. So upper Riemann integrable is infimum of upper bounds, lower Riemann integrable is supremum of lower bounds. So if both are equal, we can say given function is Riemann integrable or Lebesgue integrable. So this is what the meaning of Lebesgue integrable function is. Now let me discuss one more concept, Lebesgue integrals of step function. Lebesgue integrals of step functions. So anyhow, in the second unit we have studied the concept of step function, right? When do we say a function is step function? If a function f is defined from closed interval ab to r in such a way that if we can divide a closed interval ab into n number of partition in such a way that x0 less than x1 less than x2 so on, which is less than xn. So and further the function value will be constant, right? If a function value f of x value will be constant, then we can say constant over any integral, constant over all what we say interval, any interval, difference of any consecutive interval you are going to take in a partition, the value of the function should be constant. Then only we can say a function f is step function. So this is we have studied in previous lesson, that is in unit 2. Now we are going to express a Lebesgue integral in terms of step function. Usually step function is denoted by a symbol pi. Fine. So upper bound of a partition P with respect to step function, upper bound and lower bound represents a Lebesgue or Riemann integrals, right? So upper bound of a partition P with respect to a step function is defined as summation taken over any value within the interval I is equal to 1 to n. Fine. Similarly, lower bound of a partition with respect to step function is defined as summation taken over all the values within the interval xi minus 1. Clear? That is, both upper and lower bounds are defined in a same way, but the difference is that so lower bound of a Riemann integral or lower, what we say, this is lower Riemann integrable or lower Lebesgue integral is defined as supremum of step function less than or equal to f over all the step function pi. It is pi. Similarly, upper Riemann integrable is infimum of step function pi will be greater than or equal to f over pi. So where pi is a step function which is defined in such a way that all the lower integrable will be supremum of a step function, upper Riemann integrable is infimum of a step function. So further we can say when do we say what we say a given function is Lebesgue integral only when upper integrable lower Riemann integrable is equal to upper Riemann integrable, right? So when both are equal, we can say a function is Riemann integrable and it is denoted by Riemann integrable of a function f. So in terms of step function, remember lower integrable or lower Riemann step function is defined, lower Riemann integral in terms of step function is defined as supremum taken over all the step function, whereas upper Riemann integrable is infimum taken over all the step function. Fine. Only thing is, when we talk about lower Riemann integrable, we have to take supremum. When we talk about upper Riemann integrable, you have to take infimum. If further both are equal, we can say given function is Riemann integrable. Hope so it is clear, right? So this is what the concept of Riemann integrable in terms of step function. Now let me explain one more concept. We say it is simple function. It is simple function. Fine. Now any function f which is defined on set E to R is said to be simple only when its domain takes, or we can say f takes, finite number of values. Finite number of values. So a function f from E to R is said to be simple function only when its domain or a function f takes finite number of values. Meaning is that suppose if there exists n number of subsets for a domain E, let me take a subset as E1, E2 and so on En. So that should be finite. Whatever the subsets exist for a domain of a given function, that should be finite. Then only f will take a finite number of values. Fine. A given function f is said to be simple only when f takes finite number of values. Clear? Further, we can express E as union. That is what we can say, countable union of all EIs. And moreover, they should be disjoint. Disjoint in the sense whatever the sets, two different sets, when you're going to take intersection of two different sets, that should be equal to null set. That is the meaning of what we say disjoint sets. Clear? I am repeating once again, simple function is none other than a function f is said to be simple only when f takes finite number of values. Further, we can express E as union, a countable union of all the collections of EI, and moreover they are disjoint sets. And let me give you an example for a simple function. Every constant function is simple. Fine. And moreover every step function which will be defined on a closed interval AB is also a simple function. Why? Because all those functions take a finite number of values, and whatever the characteristic function you will define on a set of real number. The characteristic function which is defined on a set of real number is also example for simple function. fine. And moreover, a finite linear combination, whatever the function you are going to take, a linear combination of all those functions will be, as you already know in the linear algebra, linear combination of all the functions whatever you are going to take, that will be an example for simple function as it take finite number of values. So whatever the characteristic function you will define in a set of real number, that will also be an example for a simple function. So whatever the function it takes finite number of value, we say such function as a simple function. So this is what the basics of Lebesgue or Riemann integrable function is. So in the next session, hope so it is clear. So in the next session, let me continue the concept. Thank you.